Awesome. I see you're all back. So let's start with our electroconductivity exercise. So I sent you guys last night an email asking for you to download new material from GitHub. I have uploaded a data set for soil electroconductivity and also the partial code for today. I asked you to copy the data from GitHub into your data folder and the code from GitHub to your code folder. So if we're going to need that to get started here. So if you have not done that, please go ahead. And I'm going to get started just because we have some more like theory that we're going to be exploring first. But if at the time that we start coding, if you still don't have these, let me know and we can stop for a moment and so everyone can be on the same page. Okay, so I just went ahead and closed my terrain script. I cleaned my environment, clicking on that broom icon. And now, I'm still in my project. I did not close my RStudio. So again, if you're not seeing your code folder, you can click on that R blue button, go into the code folder, and then please launch your Soil EC partial script. When that happens, you can just minimize your console because we're not going to be using that. So that gives us more room. And we should be ready to get started here. Okay, so what I want to talk with you today and go through is really, start discussing and talking about what is soil apparent electroconductivity and what it is, how is it measured, and why is it even useful in precision agriculture. And once we go through some of that initial conversation, then we're actually going to get into doing the programming here. So importing that layer into RStudio, doing the interpolation, and then exporting that. And very similar, as far as the coding goes, is very similar to what we just did with the terrain exercise. We're just going to be doing that with a different layer now, which is soil electroconductivity. Okay, so I want to ask all of you, has anyone here ever worked with soil electroconductivity or apparent soil electroconductivity? So Emily is nodding yes. Emily, do you remember? So, well, can you just quickly describe how it was and what you used that for?
Yeah, so it wasn't data that I gathered, but the data was, I borrowed it from a coworker for a project in a GIS class that I took last semester. And so Soil EC, what I gathered from it, and that's the extent of me working with it, was on that project, but Soil EC tells you a lot about soil types. And so that's helpful with delineating management zones, like how much sand versus clay you have in the soil. And that will definitely, that will affect how you would irrigate those areas. And so that's how it affects management zones. If there's more clay, you would irrigate less. If there's more sand, you would irrigate more, that type of thing. And Soil EC, it indicates what kind of the composition of the soil is.
Awesome, perfect. Yeah, no, that was great because we're going to be talking about some of the topics that you mentioned there. So that's great that you have that experience. Anyone else has any experience with EC? And this could even be like, lab benchtop EC.
Yeah, I am back in my bachelor's, I was working with a team of scientists, remote scientists actually. They were trying to measure all these soil properties and plant properties to see that if they can actually identify the soil type and soil properties remotely using satellite imagery. So I did not work actually on the whole project. I just helped them with the field work. So yeah, so I went in the fields with those instruments and got the readings for the soil ECA.
What instrument did you use?
I don't remember the name exactly, but it was like a long with two what do you call it? I can't remember that. Like, two long metal rods.
Electrodes.
It was electrodes. So it would take like around 2 to 3 minutes to stabilize, but in like 2 to 3 minutes it would give you the accurate reading you need.
So it would basically have like something similar to a soil probe that you would
Yeah,
go
yeah.
in place, insert into the soil, take a
Uh-huh.
reading, and they would probably take a GPS coordinate too, and then just
Yeah,
go.
automatically it does. But the thing is, you need to give it more extensions for the GPS too. It's just not going to do itself.
Right. Perfect. Awesome. Well, that's
I have a question for, I guess, Sunab and Dr. Bastos. Is that how a Varus works? Or does a Varus, is it discs? I don't know. I've never worked with it like in the field, but
it's different. And we're going to go
Okay.
through that. And I'll show you some pictures that's going to make it easier to understand the difference. But great. I mean, I really, really enjoyed you guys' experiences because that's really going to help understand some of the things that we're going to be talking right now. Yeah, thanks.
Thank you.
Dr. Bastos, I think the most important thing to say is that there's no soil electrical conductivity, but water electrical conductivity. Everything is in the soil water, it's not soil. If you have dry soil, you cannot take readings.
Yeah, that's a great point. And you know, it's really interesting because when I was preparing for this class and reading the material to show you guys the data really behind everything, it was interesting because there was a few papers that said exactly what you said, like it's water, and other papers, I mean, of course, water is the predominant source that you're measuring that, but other sources also indicate that the solid phase, as long as it is connected, like you have a continuous solid phase that you're measuring with whatever you're using to measure, that it will still get some from the solid phase. And also something interesting is that there is, you know, I don't know the background of everyone here, if you how many soil classes you've taken, but the solid and water phase of the soil are really connected, right? I mean, as things start moving, you have gradients on mass flow and diffusion that start releasing nutrients from the soil, the solid phase into the liquid phase. So even though we're measuring the liquid phase, it's still connected with the solid phase, right? So it's still a combination of both.
Also, we take salinization problems. We can check about salinization problems in our soil.
Yes, absolutely. And that's, I mean, great. I'm loving this conversation because you guys are actually mentioning a whole bunch of things that I have in my script here that I wanted to tell you. So it's great that we're already talking about it. Okay, so, you know, if we, I left some text here for you mostly. This is not something complex, and I didn't want to just put slides together for a few things. So my way of making some slides is just adding text to this R Markdown file. And then I had some figures that I just included as graphs on the chunks that you will be able to run. But I just want to walk you through here. So what is electroconductivity itself? So it is a measure of how much electricity is being conducted through a solution. That was originally what it was developed for, right? So you would have, you know, that water that if it's pure water without any salts in it, it doesn't conduct electricity. So it's a zero electroconductivity. However, as you start adding salts to water, then now you have different charges that will conduct that electricity through. And this is really what electroconductivity is. It's just associating the amount of, well, in this case, if you think of a solution, it's just the amount of salts in that solution that are being able to carry through an electrical signal, like electricity through it. And the way that, and this is really important, and the first application of, or the first interest in measuring soil electroconductivity was, as Janice mentioned, to study soil salinity. So that is a measure of soil salinity that, depending on the value that you get for electroconductivity, you would say if the soil is if you can grow plants on such soil or not. Because if you have too many salts, the plants cannot really extract water from that soil because of the matrix potential, which then doesn't let them, they cannot really grow in that soil. Even if it has water, but it has so much soil holding the water back that they cannot grow. So the first application, or the reason why this was developed initially, was to study soil salinity and how that really impacts plant growth and adaptability. And the way that people would measure this is it would go to a field, take a soil sample, bring that soil sample to a lab, process it, extract pretty much that available salinity in that soil, and then use electrodes to measure how much electroconductivity is going through that soil, which is in relationship with the soil, the salt content of that solution. And if you think of it, how can something like that be applied in precision agriculture, right? Like it really, if you think of it, is really difficult. It's not the way that we do soil EC and that we're going to be using today. So one of the ways that people got around that is, well, sorry, I'm actually ahead of myself. Let me look at my presentation to make sure that I'm following it. So when you're measuring electroconductivity in the sense that it was originally developed, you would measure again the conductivity of the extractant that you get from a soil and water mixture that in the lab, right? And really, if we can do this in a field basis, it would be a lot, like already on the field, not have to bring to a lab and do complicated, laboratory analysis on it. It would be a lot better. So I just have here a section of a soil showing you pretty much the most important ways of which a sensor in the soil is interacting with that soil and getting the soil electroconductivity through. So the main one here is really the liquid phase, as Janice was mentioning. However, this liquid phase is also in contact with the solid phase. So this number one here is basically showing you that connection, that the solid phase is in equilibrium with the liquid phase. So we're really measuring both of the liquid phase, but also that interface between solid and liquid phase as well when you're measuring soil electroconductivity. And also, at least this source here, Janice, was mentioning that if you have a solid phase that is connected throughout as far as what you're measuring, like the volume of soil you're measuring, you also get some signal from the solid phase alone, which is very interesting. But definitely the liquid phase is what predominates in the signal of electroconductivity. Okay, and also, I guess I had this here as well to tell you that, so if you go take a soil sample, bring to the lab, extract that or make a mixture of soil and water, take that extract and then run EC, that is called electroconductivity EC, just that pretty much, or ECE, some papers use for extract. However, what we are referring to when I bring this data set to you guys today is apparent soil electroconductivity. And it is apparent because it is going through not just that liquid phase, but also integrating different components of the soil, because we're doing it right there on the field, right? So this is why it's called apparent soil electroconductivity. And the next thing I want to tell you is, okay, so we can either take this sample, take it to the lab, which is a complex process that is not very applicable for precision agriculture. But now we have ways of going to the field and measuring right there. And how are we really doing that? And what are the options that we have for measuring in situ electroconductivity? So there are three main methods of doing that. One is electro-resistivity. And I just wanna, if you run that chunk, you're gonna bring in this image here. So this is how, if you've heard of soil EC, most likely you heard about Veris. So Veris is a company that makes what I'm showing you here, and I'll tell you what's going on in a second here. So electro-resistivity is what the Veris equipment uses, where it has multiple discs. So imagine this being dragged behind a tractor or maybe like a ATV or something. It's just like an equipment being dragged on the soil on a field, throughout a field. And it has some electrodes that are transmitting the electricity. So in this figure here would be this internal one here. And then there are electrodes that are receiving that signal. So some are emitting, some are receiving. And as that electricity travels through the soil, it is interacting with soil water, soil texture, salinity, or just like nutrients overall, and is getting, so it's interacting, and then on its path, it's returning to a receiving electrode that by that difference of what's coming out of the transmitting and what's reaching the receiving electrode, it has a measure of electroconductivity, right? So how much is being conducted from the transmitting to the receiving disk. And these are difficult to really notice, but these are not, it's not like an injection needle, is an actual disk that is going through and interacting with the soil. Again, this type of method, which is electroresistivity, is used mostly by various equipment, and is the way that the data set that we're going to use today was using this type of methodology. And this is really useful because at the same time that is taking those measurements is also taking a GPS coordinate, right? So you know where in the field this is changing. And something else that the electroresistivity system has is that depending on the distance from the transmitting to the receiving electrodes that you have on those disks, that would dictate how far into the soil that signal is being related to and averaging over. So the closer the transmitting and receiving disks are, the shorter soil distance or the shorter soil depth is being incorporated into the measurement, and the farther apart they are in that cart, the deeper soil layers are being incorporated. And the way that it varies works is it has a set of close together and farther apart disks that it does give you a shallow depth EC and deep soil EC as well. So we do have those two pieces of information from the various. This is just something that I wanted to bring up because we'll see these columns in the data set, and I just wanted to understand how they're really working.
Dr. Bastos, does a Veris, it also gathers elevation data, doesn't it? Or
Right. So
does it? Okay.
Yeah, I think the minimum, so I mean, there are different various products. I think that the least complex one gathers elevation and then EC at 2 depths. But there are some more complex and also more expensive various systems that would give you those two things, and also like organic matter, nutrient, soil pH. So different things are being measured on the go, depending on what various system you have. The one that we have that we're going to be using today has the EC at shallow and deep layers and also elevation. That's the data we got. Okay, so the next one that I want to show, the next way of measuring soil EC on the go is electromagnetic induction. And I just want to print this here so you can see what it is. So this is really, you can think, I mean, this figure is showing us the soil, so a top soil and a subsoil layer, and then this like rectangular thing that it would also be an equipment that is dragged on top of the soil. And the main difference here, or one of the main differences, is that it does not have discs. So it is not cutting through the soil like the electroresistivity equipment is. So this is just sitting on top of the soil and it's still being dragged along the field. And the way it works is there is a transmitting coil that sends the electromagnetic signal, and then this interacts again with soil, and the return of that is read by the receiving coil. But again, the main difference here is that this does not cut through the soil. So it's not invasive in that sense. But on the other hand, it has some pros and cons. So for example, here, we do not really have the control of the depth that we cannot control the depth that this is sensing. It's pretty much a fixed depth for whatever distance this is, these two coils are. Whereas with the varies, you can really play with that and change the distance, even though they come set up to measure two distances that are already related to root zone depth. So it's not like you would really want to change those depths, but the varies or the soil resistivity approach gives you that option of getting different depths, but it does cut through the soil. So it has that component, that invasive component that the electromagnetic induction method doesn't. And one commercial example of the induction method is what's called Geonyx EM38. This would be the name of the equipment. And then lastly, the other way of measuring soil EC on the go on the field is with time domain reflectometry, which is also called TDR. So if you heard of this, probably you will remember the name TDR. And I just have a photo here to show you. Even though it is mounted on a tractor, but you can see those two electrodes there, which is what Sunab was referring to, I believe. That, even though this is on a tractor, the tractor is stopping there, it is deploying the sensor, bringing it outside of it, and then moving on. So it's not like an on-the-go measurement like the previous two ones. And even though I'm showing you here this figure of a tractor doing this, one of the other most common ways of TDRs is like a handheld device that looks like a soil probe that I think is probably what Sunab was also using, which then you just insert into the soil. It also has those two prongs that send a signal through it and then reads whatever is coming back on the other probe, and you just take that. So it is in situ. It's not on the go as far as you're just dragging equipment and getting on the go measurements. You have to actually have a person going there, inserting this into the soil, removing it, and keep doing that multiple times. So it involves a person doing that manual work of actually getting the data. I mean, of course, the other ones also require a person to drive a tractor or something to drag that equipment, but this one is a lot more time intensive and not as scalable as the previous ones. Okay, so one thing that's really important to notice is that are different soil parameters that impact soil apparent electroconductivity. One of them, as we mentioned, is soil salinity, right? So, well, let me ask Victoria. Victoria, I'm going to tell you that soil salinity is related with soil EC. How do you think do you think that one goes up, the other goes up, or a negative relationship?
No, I believe they're directly related.
Awesome. Yes, that is exactly it. So if we just print this or run this chunk here, we're going to see that. So on the y-axis, we have ECE, which is the EC of that extract from like a soil that is taken on the field, taken to the lab, and then extracted the solution. This is what ECE is, and ECA is the in situ measurement. And we see here that as the actual, and ECE is a measure of soil salinity that you would do would be the golden standard to compare to. So we see that as ECE is increasing for different soil types, ECA, so the in-field measurement is also increasing. So the more salinity you have, the larger soil ECA you're going to have as well. Okay, so it is also affected by soil texture. So now let me ask somebody else. Let me see here my Zoom people. Maybe I'll send this on Span's way. Span, are you there?
Yes, sir, I'm here.
Okay, so how do you, if I tell you, like if we think of, let's compare the two extremes of texture, right? So let's think of a clay soil and a sandy soil. Which one do you think would have the greatest soil electroconductivity?
These are the finer clay soil because the particles are smaller and there's less space between them.
Perfect, that's exactly it. Yes, so smaller particle sizes like clay, they have more surface area, they have more sites for exchanging cations and anions with the soil. And so that's exactly it. We see here, so it's calling conductivity, but it is electroconductivity in millisiemens per meter. And we see that clay soils have a larger value of conductivity as compared to sand. Just because exactly of what Spen was saying, if you have more clay, you have more sites to interact with nutrients and salts in general, if you think of nutrients as salts. So you would have more salts in that soil that would conduct more electricity if you measure it. Perfect. Okay, so let me send this someone else's way. What about soil water content? Maybe I'll ask Emily.
I would think that the higher soil water content, the higher the electroconductivity.
Yes, and that's exactly it as well. So here we have on the y-axis ECA, and then on the x-axis volumetric soil water content. And we see that as water content increases, ECA also increases. And here we just have some different curves for different aspects of the conductivity of the soil solution itself, which I don't want to get into. Just wanted you to look at the overall picture of this, where that's exactly true. And this is, so all these things that we're saying, right? So soil water content affects the reading that you get. Texture affects it, and salinity affects it. So if you think of it, of these three, soil water content is really the more dynamic one, right? So soil salinity is somewhat fixed unless you're really managing against that or to mitigate that. And texture is definitely fixed, right? At least in the short term. So the one that's changing is soil water content. And this is important because if you're using any of these instruments to measure soil ECA and you want to use that for precision agriculture purposes, you have to keep this in mind. Because if you have a field that, let's say you for some reason, you have half of the field irrigated, the other it didn't irrigate, and then you run a variance there, this is not going to be good quality data. Or even if you have such a high variability in soil texture that affects soil water holding capacity, that could also confound your effects, right? Because your texture and water are mixed there. So this could make it more difficult to really use this data. So it's not like you can go to whatever field, run a variance and use this data without having to think about it. There are some planning steps that we have to think of and make sure that we collect the best data possible to then use for precision agriculture. Because if you collect bad data and you bring into using precision ag, you're not going to get good results. So just wanted to keep that for you all to keep that in mind. And also there are other things that also impact the reading that you get. So soil temperature is one, soil organic matter content, and soil bulk density. I didn't want to show a graph here because they're kind of like more on the secondary variables that impact, but the most important ones are the ones that we talked about. Okay, so last talk before we get into the code here. Why is soil EC useful and important in precision agriculture? As Emily was mentioning earlier, soil EC, and also we saw here with the graph and with span explanation, soil EC, if collected properly, will give you a good idea of your different textures across a field. And why is then texture important? Right? So if you think of it, texture is really very correlated, linked with things that impact yield. So nutrient, so cation exchange capacity, nutrient availability in that soil, water availability, right? So if we have, well, if you think of sand, water availability is the least that we can have because that water is not being held as strongly to the soil, it's just going through it. And then on the other side, if we have a very heavy clay soil, then it holds water so tightly and it doesn't drain as much that it can also negatively impact yield as well. So the relationship of water availability, cation exchange capacity, and nutrient availability that are linked with texture is what we really gather from these soil EC measurements, and that's why they become useful. And I just want to show you here a last figure where it was a paper where these authors were relating EC and yield. So, I mean, there's lots of colors here, and I really don't want to get too much into, everything that's going on, but I just want to highlight here that where they observe low EC values in the field was also related with low yield for this field. And similarly, where they had high EC also had higher yields. And, these are not gray maps for us to really look at because they don't really have a legend. So we don't know how much minimum, maximum, and colors mean, but the overall relationship of EC and yield is what I wanted to show you. And also wanted to make the point that in this field here, EC and yield were positively correlated, at least what they're showing here that we can gather from this figure. But that does not necessarily mean that it will happen for every field every time. Sometimes, depending on the weather, you can have the opposite relationship. And we talked a little bit about this in a previous lab where, if you think of a part of the field that has more clay and just holds on to water more strongly, if you have that in a depression, this area will probably yield better in a dry year, but it could be just in a wet year, it could be just so wet and flooded that would yield poorly in a wet year. Sorry. So there's a relationship, right, between EC and texture and topographical position that correlate with weather impacting yield in the end, that we just have to keep in mind. It's not always low EC, low yield, high EC, high yield. It could be the opposite as well. But I just want to give you one example of that.
Dr. Bastos,
Yes.
is it okay to say that high ECA can also mean high salinity and that can actually hinder the plant growth?
It could, yeah. So, and again, this is a very field specific, right? So soil EC data is very field specific because you have to know
The texture and
what is like for that specific field, what is EC really telling you? Is it being controlled by texture or water or perhaps salinity, right? Overall in ag fields, if you have a field that has received even water applications or just like even rainfall throughout the entire field, and you don't have salinity problems, then EC will most likely be controlled by texture, which is what we want, right? But as you're saying, if you go to a saline field or sodic field and you use EC, it is probably being controlled by salinity and not texture, right? So that's where like soil EC mapping is really field specific, and you have to know about that field before really making use of this information.
Thank you.
Yeah. Any other questions or thoughts? All right, so let's get to our data part. I left you here all the packages we're going to be using today, so you can just go ahead and run. And again, if you don't have some of them, feel free to on your own install using the install.packages function that we've been familiarized with already. And then I also created that same my theme map object for us to be using throughout the different maps that we'll be creating. So you can just run that. That should appear on your environment. Okay, the first thing that we're going to do then is just to import that EC layer. And so if you recall, when you copy and paste it to your project, that was a CSV file. So because it is a CSV, we're going to use read_CSV and then open and close quotation marks, .. / to get outside the Go folder, tab, data, tab, KB2_ECA. That's the one that we want to import. Okay, just going to import that and then print it. And look at this. It is such an interesting data set. This is, another aspect that of just like having your column names being, short, but also informative of what they mean. So I got this data set and I was looking at it and I was like, I can probably guess what these columns are, but I don't want to do that. I want to really know exactly what they are. So I asked George about it, and then he confirmed to me that F1 and F2 are the coordinates. We can kind of guess just from the number that they are, especially if you compare it to the other fields that we know, those are the coordinates. And then F3 and F4 are the soil EC. So F3 is soil EC shallow depth, and F4 deeper depth. So the shallow is 0 to 30 centimeters, and the deep is 0 to 90. F5 here is elevation, as Emily was asking and making the point that they also collect more data. And then it has this ID column that is really not useful for us. And overall, this data set has over 8,000 rows. So it took 8,000 measurements of soil EC at 2 different depths for our field of interest. Okay, so if we come here to the wrangling part of it, something I always like to do, and I guess it's somewhat up to your personal style. I think it's really useful if you do the clean names function just to get everything lowercase. And that is helpful in programming, because if you have uppercase, sometimes we have to have uppercase to differentiate some things, but if you don't have to, I think it's useful to have everything lowercase, because it's one less key stroke that you give to give upper and lowercase, so it just saves you a little bit of time. But if you're doing this a lot, it's useful. So after the clean names, I left 3 dots there because I want to work with you on this. So you can just delete those three dots, and we're gonna basically select functions and rename them as we were doing previously. So again, to do that, we do the dplyr colon to make sure it's coming from that package and use a select function, excuse me, function. And I want to do this. So these are the columns that we have right now. I want to take F1, but I want to call it something else. So to rename it, I want to call it X. So we say X equals F1, comma, I want to do a return just so we can see better. Y equals F2, because those are the X and Y coordinates. And then I want to call the actual ECA columns, I want to call them ECA 30, because the first one is the shallow 0 to 30 centimeters. So I just want to add a 30 there. And then I also want to add the units. So underscore, the unit is in deci per meter. I just want to do DSM all lowercase, just so we remember. Because the one thing is, there are different units that can be used here. So the other common one is millisiemens per meter. I just want to make sure that we know what is this unit here. And so this column here would be the F3. So ECA 30 underscore DSM equals F3, comma, hit return. And then we're going to do ECA 90 underscore DSM equals F4. So F4 is the ECA at the 0 to 90 centimeter depth, also in decisiemens per meter. And this is pretty much all I wanted to do here in the select. Don't forget to add the pipe after it so it connects with the code below. And then what we're doing next is really something we've been doing a lot already with other exercises. So just transforming this into an SF object and saying what columns contain the spatial information. And these values here are in WGS 84, which we're just assigning that CRS at this line of code, and then transforming that to NAD 83 UTM CRS in the end. So if you run it, and then we're saving all this to an object called ECA underscore W, and the W is just for us to know that is the wrangled version. So if we print it now, we notice that it is a simple feature object. It has NAD 83 UTM zone 16 north that we wanted. And then the data set has now the ECA at 30 and 90 decisiemens, or 0 to 30 and 0 to 90 centimeter depth in decisiemens per meter. All right. Okay, so this, and I want to stress this again, because this is the workflow that I do for every single project I have, regardless of what it is. I bring in data, I wrangle the data, I do EDA, which is exploratory data analysis, which is basically to look at this data, see if it makes sense, if you're missing something. And then only after that, I really do whatever I want to do. In this case, the next step after that is interpolation. Right, so this workflow here is really useful for any analysis, including your own experiment analysis when you're going through that. So I just wanted to reiterate that. Okay, so for what we're going to do here is we're going to start with the ECA underscore W, add a pipe, and then feed this data set into a ggplot call. So this is exactly the same as doing ggplot data equals ECA W. Just wanted to, oops, lowercase. But I just want to show a different way of doing this. And now remember that when you're within ggplot, you did not use pipes, you use plus. So let's add a plus, hit return. And I want to add a geom SF because ECAW is an SF object. And I just want to color here the data points by the ECA 30 column. So we do that by specifying the statics function. And then I want to say color equals ECA 30 underscore DSM, which is a column name inside the ECAW dataset. And I get outside of the AES, add a comma, and I just want to say size equals 0.5. So this is the size of the point. This is what I decided to have. If we just run this, this is what we see. I just want to do a couple more quick changes here. So one of them is to add the plus. I want to change this to a scale underscore color underscore virides B. we run that, we just change the color. And also, I just want to add a plus, and lastly, add our theme. So my theme underscore map, just to make it look like we want. Okay, so this is basically just exploring that first depth, the ECA 0 to 30 depth. And we see here that values are ranging, I mean, at least the breaks are ranging from 3 to 9 decisiemens per meter, which makes sense. And so lower values would be coarser texture and higher values would be finer texture. So we see a whole bunch of coarser texture on this east side of the field. Okay. So next thing, I want to do the exact same thing, but with the 90, 0 to 90 depth. I left you the code already, so you don't have to type anything. You can just go ahead and run it, just so we can see. And you know, I want to ask you here. Well, I'm just going to go ahead and say, I guess, if you notice the 0 to 90 depth EC data has higher values, right? So now is the breaks are going from 4 to 12, and for the shallow layer 0 to 30, we're going from 3 to 9. So we do have higher values here, which now I'm going to ask somebody, what does that mean? What does it mean that the deeper depths has higher values? What does that tell us about texture?
The soil is clay, more and more clay, that the water doesn't let go more down. That at the higher depths we have, at more depths we have more clay soil.
Right, that's perfect. Thanks, Nab. Yeah, so that's also how I would interpret it. At higher depths, we have more clay than we did at shallower depths. Yep, awesome, thank you. Okay, so next thing is, you know, we're going to do the interpolation of both of these layers. And as we know, to do interpolation, there are a whole bunch of things that we have to do before that. The first one being importing the boundary and transforming that to UTM N8083 zone 60 north, which is we're doing right there. And then creating the grid based on the boundary with a cell size of 10 by 10. And again, our cell size is remaining constant throughout because we want to use all of these layers to match in the end, so we can do some analysis with them. So you can just run that chunk. There's nothing for you to type in there. And again, just doing this rough plot of the grid as a raster, which colors by ID, which for us is really not useful because it's just each cell has an ID. So, I mean, it's just a default. I just wanted to plot to show that it is there. And then we're going to do the interpolation of each one of these layers. So the first interpolation that I want to do is for the shallow layer of 0 to 30. And if you recall, I left 3 dots there because I want you to write out the name of the column, right? So just remove those 3 dots and let's just call ECA 30 underscore DSM. So we are interpolating these points. Oh, and also you can stay right here. You don't have to move. I just want to make a point that maybe I forgot. So these maps, even though they seem pretty continuous, but they're really not. These are points, right? It's point data, and we can kind of see the path with the turns at the end. And one way to also inspect that is just decreasing the size of the point. I just want to do this for one plot so we can see. So now with a smaller plot, a smaller point size, we can really see the point data being collected and the turns that the equipment, the various equipment was taking when this was being measured, right? So because we have point data, we want to interpolate that and have a continuous layer. That's why we're doing interpolation. Okay, so coming back to the chunk where we were, you can just run that to create the model for interpolation of that shallow depth. And then you can just run the next chunk as well, which is just predicting. So this is the one, this is the chunk where the actual interpolation happens, right? So if you just run that, it's going to take perhaps a moment. And then it gives us a stars object with the, again, remember that I was telling you the var1 pred name is coming from that predict function of the IDW algorithm. It's just how it changes the name of the variable. But we know that in this case, var1 pred is the ECA 0 to 30. And then we see that it's varying from 0.6 to 8.5 decisiemens per meter for the shallow depth. Okay, so now I want to make an actual nice looking map of the interpolated ECA data for the shallow depth, which I have.
I'm so sorry to interrupt. Can you please go up a little bit? I just kind of got mixed up on the making up the model. So
Right here.
yeah, I'm so sorry.
Yeah, no worries. Please, I mean, I appreciate that you stopped me because I do want you all to follow along. So that's important.
Yeah, I got it. Thank you so much.
Awesome. All right, so let's get back here and make our map. So this map I do want to save on an object because it's not just EDA, it's not just exploratory data analysis, it's actually a map that I want you to save to file. So let's save that to this object called ECA30 map. Let me look at my cheat sheet here. And we're going to start again with a ggplot call. We add a plus after that, hit return. We're going to use a geom_stars. So notice that on the first plot we made for EDA, we used geom_sf, right? Because it was a point vector data. Now we have interpolated. So now it is a raster file or a raster object of type stars. And that's why we use geom_stars. So we're going to do data equals, you can come up here and copy and paste because it's kind of like a long name. So ECA30 IDW pred, that's our data for the geom_stars. If you just run that again, let's just explore quickly. This is what we're seeing. So we see that like more checkerboard type of look because of our grid, right? Our cells. And I want to do a whole bunch of changes here to make it look nice. So the first one, I want to add a plus and include a scale _fill _virides B. If we just run that and paste, this is what it looks like. Okay, next thing is I want to add the boundary. To do that, we do a plus geom_sf, right? Because boundary is a vector of type SF. And we say data equals boundary _w. And we have to say, well, let's just run this way. I want to show you why that is not a good idea. Because our boundary basically has a fill, and so it covers what's behind it. So we have to come back here, add a comma, and say fill equals not available. And then that lets us see through while still having the boundary outline. Okay, so next thing, I want to change this var1 pred name. Because this var1 pred name is being controlled in this plot by the fill, we use the labs function and we say fill equals open and close quotation marks ECA 030, just so we know it is the 030, not 090. And then I like to include units on my legends. So DS for decisiemens per meter. Okay, so that's how it will look like. We can run it and print it. So it is starting to look a lot better. One thing that I dislike about the way that it's showing that ECA 030 decisiemens is that it is a long name and it's taking horizontal space in our plot. And what I want to do is break line. So basically break line between ECA and 030 and 030, and again between 30 and decisiemens. To do that on this type of, like when you're doing with a string like we have here, like a text string, the way that we do that in R understands that we want to break line is to add a /n. So if we just do that, and it's okay if it is touching both ECA and the 030, or if it's not, I mean, it really doesn't matter. But I want to make it touching because then we have less white space afterwards. And if we print it, we see that it broke line right there. And I want to break line again after the 030. So /n. And then we basically broke the length of our legend to something smaller and more concise. And then lastly, I just want to add a plus and include our theme, which is called my_theme_map. We just run that and print it. This is how our final map looks like. Okay, I will just leave the code for a moment up here so anyone that needs can catch up. All right, and let's move on. So we're basically going to do now. So this, again, the interpolated shallow EC map. We want to do the same thing for the deep EC map, which is the 0 to 90 centimeters. So we come here to the next chunk, and we're really just going to change. So I want to print below here the data set just so I have a reminder of the name of the column. It's right there. I'm just going to copy that from here and paste up there, or you can just type out if you want. And then but make sure you do bring in the 90 centimeters here, right? Because this is a different layer now. So we can just run that and print. Again, I left you the code for actually running the IDW with the predict function. So you can just run that. And then we see here that for the deep soil layer, so 0 to 90 centimeters, it is ranging, the interpolated values are ranging from 1.7 to 14 decisiemens per meter, which we already were expecting that it would be higher than for the shallow that was ranging through 8, I think, like 0 point something through 8 point something, which is what we saw also on the vector point data that we brought. And then I also left you the code for the plot because it's basically the same as the one for the 030. The only difference is that the data set coming in is different, right? It's for the deep layer. And also the label here, I made sure to change from 0 to 90. So if you just print that, this is the map we get. And because I think it's really nice to have them side by side. I like to, so again, even though we're not loading the package right here at this chunk, but the package patchwork was loaded on the first chunk of the script. And that's why we can do this like ggplot object plus ggplot object, and it understands what to do with that because the patchwork package. So we're doing that first and then saving this to our output folder and calling this soileca.png with width of 6 and height of 3 inches. So if you just run that entire chunk and you come here on your files tab, go to the R output and check soil ECA, you should see something like this. Right, so now side by side is really a lot easier to see how those texture differences are happening at 2 different depths. Okay. So now again, these are still raster, right? And we want to do the grid extraction. Let me just get to my code here. Yeah, so to do the grid extraction, you just come to this chunk. We use that assignment symbol. We're going to start. So this is for the 0 to 30 depth first. So the object that has the raster values that were interpolated for that is the ECA30 _ IDW _ pred. So remember pred, not mod. We add a pipe. Again, because we're extracting to the same size of grid cell, which is 10 meters, we're just going to transform this from raster to vector using the STSSF function. It has that argument called S points. We want to say equals false, S _ points equals false. So it gives us the polygons rather than points. And then also has that argument called merge that we're going to say merge equals false. So it gives us one individual geometry for each polygon. After that, add a pipe, we're going to use a select. So as you know it, we're coming from the dplyr package. So dplyr : select. And here I'm just going to rename, because right now, if I just print this, we still have this column var1 pred, right? So I would just want to rename that to ECA 30 underscore DSM. So the same name we used before equals var1 pred. So we rename the column. And again, we add a pipe. And lastly, we're going to use the row names to column function. And the argument var equals open and close quotation marks ID. So we just did something very similar, or exactly the same thing really, for the terrain exercise. So what we're doing here is just bringing that row name, which is the ID of the row, and making that as a column so we can do a left join between the shallow and deep layers at the end, and then export that combined object, just as we did for the terrain exercise. Okay, so all done for the ECA 30. Now let's do that for the 0 to 90 depth. I already left you the entire code, so we can just go ahead and run it. It's the same code as above, just the difference is that the incoming data set is different. And then we're changing the name to ECA 90, so we know the difference between the depths on the column name. Okay, so next step and nearing the end here is really just to merge both of those layers. It's going to be the same way as we did for the terrain. So I'm calling this ECA underscore V for vector. And we're going to start with the ECA 30 underscore V object, which is again the one that we just created above. Add a pipe, hit return. We're going to start with a left join, just like we did before. And inside this left join, we're going to have the ECA 90 underscore V object. But remember, if we just do this, it gives an error because it's saying we should be using a different function. That's exactly what happened before. And if you recall before, my workaround for it was to transform this ECA 90 to as data frame first, right? So I'm just printing this for you to see. This is forcing that ECA 90 that was a SF object into a data frame. And this data frame still has that geometry column, which I want to remove. So to do that, we add pipe and we do the dplyr : select minus geometry. So we remove that column. And if I just run this for you, so you can see the output, this is what we're merging, or let me use the word join, that we're joining with ECA 30. So if you run this and you print it, now we have an SF object with polygon geometries that has the ECA 30 and the ECA 90 interpolated values for our field. And also something for you to notice, you know, we have already mentioned this a couple times or a handful of times, but we are expecting for this to have 4,032 observations because those are how many cells there are in our grid. And this again is the reason for this grid, because we're forcing every layer that we bring in to match that grid. So in the end, they all match in spatial resolution and also extent, right? So this is also something good to check, that we do have those number of cells on these final products. Okay, so now we're basically just going to export this. So we're going to save this object that we just created to our data folder with the name ECA underscore V and with an extension of GeoJSON. So we can just run that. I get an error because I have already done this before. You should not get an error. Oh, and then this is pretty much the end of our coding exercise here. So just very quickly, I want to tell you again, just to summarize, I know we did a lot of stuff today and it can be overwhelming. I totally understand that. So I just want to quickly run through a summary here. So what we did in this ECA exercise was, again, to import the point data of soil ECA. We did some wrangling, we changed some names of columns, and then we interpolated both the shallow and the deep soil ECA data to our grid that we've been using for all other layers as well. And then we transform them into vector, join both of those in one object, and exported this one object that has the ECA interpolated data for 2 depths, and save that to file. So this pretty much ends our data gathering processing step, which was a long step, right? Maybe almost 2 months, I don't know, a month and a half. So it took a long time, but this is what you would do in, if you work in industry and you're doing this type of work, even if it's not in art, right? Because this workflow here, the framework of this is really applicable to any software. It's that you gather data, you wrangle the data, you process it. In our case, mostly processing was removing erroneous yield data points and doing interpolation. And then you export that. So in the end, you can bring all those process versions together and do zoning, right? This workflow here is really applicable to any situation, including commercially or in research. And so with this, again, we finalize our data gathering processing step for my part of the class. And the next step now is really going to get into the management zone creation and validation. I have a couple different ways that I want to expose you to, which I don't think one of them, and I just want to quickly browse through that. The way that people do management zones is they bring a whole bunch of variables like we have here, for example, yield stability, terrain variables, soil EC. If they have more data, they can bring that too, as far as it is geospatial data. And they give all this data to an algorithm that's going to cluster this data into groups that are similar inside of that group. So all observations in a group or a zone are similar, but they are different when you compare zone A to zone B. So zone A and B are different, but within zone A, things are similar. Within zone B, things are similar, right? So this is normally what happens. Some of the algorithms that people use are like k-means or fuzzy k-means, something like that, which is like an unsupervised algorithm. And I'll get more into what that is and what it means in the next exercise. But I also want to expose you guys to a supervised exercise, which is going to be to use a tree algorithm to understand what is driving the zones, but also the yield stability areas, and even see if the zones that we come up with are even matching to some extent with the yield stability areas. So that's something that we're going to be doing next. I know I said a whole bunch of words that maybe you have never heard of before, like supervised, unsupervised, clustering, all that lingo, but do not fear, we're going to go through this a lot slower in the next exercises. But I think this is, at least I'm very excited for this next step. I have not prepared the script yet. I'll be working on that probably today or tomorrow. And so I don't even know what's going to come up of this. Maybe we're going to have, I don't know, very nice results with like three or four or however many we need, very distinct zones. Or maybe it's going to be different. It's going to tell us that really we don't need zone, which I don't think is the case for this data set, because we know that's very highly variable in spatially. But I'm very excited about this next step and even see what the results are, because I don't know what they will be at this point. So hope you're excited too. And if you guys have any questions, now is a good time to ask them. If you don't have any questions, I think we are all wrapped up today. So I will be preparing the script and uploading to GitHub sometime before our class on Friday. So be on the lookout for that, and I'll see you guys then.